All right, so today is lecture 10, and the topic for today is called uncertainty quantification. So I'm going to share my screen, and I want to refer us back to our map. Remember, this is the course map, so we understand what's going on in this class in space. I'm getting my wires crossed. Spacecraft navigation. That's the name of the course we're doing right now. Sorry, it's been a long day. So we have our course map. We started with orbital mechanics. We are done with that unit now. Orbital mechanics is behind us. We all understand how to do orbital mechanics. You'll also notice that for the most part, each of these units corresponds to a homework assignment. So we had an orbital mechanics homework assignment. Next is estimation theory, which is kind of represented by this abacus. This is going to be kind of a math-heavy part of the course, and it might feel like we're not learning that much about space for a little while, but what we're doing is we're kind of building the tools and the mathematical framework that we need to later do some of the cooler stuff that we're going to do. So if y'all are familiar with the movie Karate Kid, this is the wax on, wax off portion. You know, you do a bunch of menial chores, and then after a while you realize that you know karate, and that's basically what we're doing. So the estimation theory portion of this course, which will be at least the next 3 or 4 lectures, probably a little bit longer, is going to be wax on, wax off. And hopefully it's at least moderately interesting. And then this will be the groundwork for some of the fancier stuff that we do moving forward. So today's topic is called uncertainty quantification. And I want to start off with a quote. So when I was a young RPI student, actually I started off as a community college student. There's a community college just down the road called Hudson Valley Community College. And during my 3rd semester at Hudson Valley, I was cross-registered taking some Hudson Valley courses and some RPI courses. And I took a weed out course, which was very challenging, and I was unprepared for it. And I wound up, doing okay, but with more effort put into it than I had ever put into a course before. And I found myself at one point in the middle of a 8-hour long lecture study session in the library at RPI, which turns out that's actually pretty common at RPI. We have a lot of marathon study sessions, and we were in the Richard Gilman Folsom Library where the concrete was poured so it looks like it's wood paneling and it's very 70s. Somebody had scratched into the wood or into the concrete in one of the study rooms, and it was kind of obscure, like you had to really be staring at it to even see that something had been scratched in there. But the person had written, "I don't know if I ever knew anything." And it just kind of felt like the insane scrawlings of a madman. Watching, like a journal you find in a cave next to a skeleton. It's like, what is this? It sounded like someone just coming unhinged. I don't know if I ever knew anything. And that was my introduction to RPI as a school. Some of y'all might have had a similar experience. And so the the reason I tell you that story is to say that the basic question we're trying to answer with uncertainty quantification is this: how do we know what we know? And then, to be a little bit more specific, because this is a quantitative analysis, how well do we know what we know? So you might be familiar with terms such as standard deviation and variance, and maybe even covariance, which are numbers that we give to describe the distribution of some set of numbers. Or if we're talking about random numbers, can even give us a little bit of information about the probability density function. And so, if those sound a little bit familiar, that's basically what we're going to be talking about today. We're going to be talking about covariance as it pertains to spaceflight and spacecraft navigation. And also, by the end of this lecture, hopefully, we will have a slightly better understanding of eigendecomposition, because we will be doing eigenvalues and eigenvectors in this class. And I remember, for some of you, I'm sure you're already experts at that, but for me, when I first learned eigendecomposition, it felt like some sort of witch's spell that we were casting on a matrix, and I really didn't understand why what we were doing worked. And it was actually this class, when I took the equivalent of this class 6 years ago, that really finally made everything fall into place. And I was like, oh, eigen decomposition is so cool. It's such an incredible tool, and it's super duper useful, and it's so simple. And I just, it's sometimes something's been explained to you 9 times and you just need it explained to you a 10th time. But hopefully today's lecture helps with that a little bit. So we'll get into the material then. So a random variable, random variable, we're going to call that RV, not a recreational vehicle, but a random variable, is a variable whose value is subject to stochastic variations. And somebody who has been studying their SAT vocab, what does stochastic mean? Any takers on that one? I have to look that one up.
It means there's like some error.
Error, or in this case, it means basically random, that there's a certain amount of uncertainty involved in it. Very good. So I guess in this case, it's dancing around using the word random in the definition of a random variable, right? Because you can't use a word in its own definition. But there is uncertainty. And yeah, error, uncertainty, randomness, these are all kind of similar concepts that we're going to be exploring today. So thank you for chiming in with that. Basically, a random variable does not have a single fixed value. So it is not a number. It's a little bit like the Heisenberg uncertainty principle. It's like a cloud of electrons where you don't fully understand what's happening in there, right? That's a little bit like what we have. A random variable is like this cloud of electrons where we don't fully understand what's happening in there. Instead, rather than knowing what a random variable is, a random variable is described by a probability density function, or PDF. There. I guess that should probably be capital. When I think of PDF, I think of like, the files on your computer. PDF. Probability density function. So a random variable, and this is going to be a word heavy lecture today. Apologies for that in advance. Random variable is a fantastic tool for modeling something that we think we know, but we cannot be certain. For example, say a spacecraft state. So we will not, in this class in general, be solving for a spacecraft state. We will be estimating a spacecraft state. And we understand that that spacecraft state is actually better modeled as something where we have an estimation of its value, but it also comes with an uncertainty, right? So a PDF, probability density function, describes the likelihood of a random variable taking on a particular value. So because when we ask what the value of a random variable is, it has to be something. So because a random variable must be something, then the integral of the PDF must equal 1. Hopefully that makes sense, right? The function that describes the likelihood of a random variable taking on a specific value needs to add up to 1 exactly, because in general, there is a 100% chance that it will equal something, right? So to put that in terms of mathematics, we would say that the integral from -infinity to infinity of, we're going to use lowercase p of z dz is equal to 1. Okay, so far so good. Where might be obvious, but we're just going to make it explicit. P of z is the PDF describing a random variable z. This is where it's going to get a little bit tricky, because in general, and this is something that we're going to be doing, at least in this lecture, a capital letter denotes a random variable, and then lowercase denotes a realization of a random variable. What's tricky is that the letter Z lowercase looks an awful lot like the letter Z uppercase. So I'm going to go out of my way to make my capital case Z's very large. But if it's ever not clear, go ahead and just throw your hand up, ask a question. I guess don't throw your hand up because I won't see it. But go ahead and ask a question. That would be good. So next, we introduce the expected value operator. Some of you might be good friends with the expected value operator. Some of you might never have met it before. It's very friendly. Expected value operator looks like that. It's E of something, where the dot is just something, right? So the expected value of big Z, that's a big Z, is equal to the integral of Z P of Z dz. That's the formal definition. The more informal definition is it is the thing that it is most likely to be. That makes sense. Maybe that's a little bit kind of sloppy. It's the expected, literally the expected value. You know, if we were to randomly draw from this, the expected value would be what we get. It is essentially, not to get ahead of ourselves, we're thinking in the direction of the mean of a distribution, right? So the mean of your distribution is going to be related to our expected value. So E of Z is the expected value of Z, sometimes called the first moment of the distribution, or simply the mean. So I kind of fibbed before. It's not related to the mean, it is the mean. The expected value of a distribution is the mean of the distribution, right? So we can observe, first of all, that the expected value operator, E, is a linear operator. Those of you that are new to graduate school might be learning this for the first time. Some of you, especially people who have taken systems analysis techniques, will have heard this before. But a linear operator needs to satisfy what's called superposition and also what's called homogeneity. And so the idea is that a linear operator can, well, it's better just to write it out as an equation, right? So this, you can sum it all up like so. The expected value of a plus b z, where a and b are just two numbers that are not random variables, and z is a random variable. Well, first of all, we're allowed to split it up like so. E of a plus e of bz. And then also the expected value of the letter A, or the number A in this case, which is not a random variable, is just itself, right? The expected value of the number 2 is the number 2, right? Similarly, this would be written as B times the expected value of Z, right? And so if you can say, what is it? The function of ax plus by is equal to a f of x plus b f of y. That is the minimum necessary qualification for superposition and homogeneity. If y'all are interested in that, doesn't necessarily mean much to us that it's a linear operator, but this is very important, right? The expected value of a number that is not a random variable is itself, and if you have something multiplying a random variable, you're allowed to move that outside. It's a little bit like the way you're allowed to move a number outside of an integral if it's not a part of the integral, right? You can move like a constant outside if it's not part of like x or whatever it is that's being integrated over. So we'll note something that I just said out loud, but I want it to be in the notes. Note that the expected value of a regular number that is not a random variable is just itself. And I would hope so. Be weird if it wasn't. So scroll down a little bit, make a little more room. So we're going to say that this term mu, which I'm introducing, which we got to be careful. This is not the mu from orbital dynamics. This is different. Mu, which we're defining as the expected value of z, is the first moment of z about the origin. Then we will define clean that up a little bit, lambda superscript k as the kth moment of z about the mean. So now we're no longer asking information about the way the probability density function is grouped about the origin. We're asking information about the way it's grouped about its own mean, right? So we'll say that lambda k, actually, you know what? Sorry, I know you already wrote this. You can keep it in your notes if you want to. I'm going to drop k down to be a subscript. I just like that better. That's my preference. My apologies if you already wrote that in ink. It really doesn't matter. It's kind of just the way you choose to write it. Lambda sub k is equal to the expected value of z minus mu. Or you can think of it this way. This is equal to the integral from negative infinity to infinity of z minus mu to the power k, p of z dz. Okay, and so we can think about this for a little bit, and I'll allow you, this is going to be an exercise left to the reader, but as defined, lambda 1 is equal to 0. So that's the first moment of z about its own mean is equal to 0. And I'll let you kind of convince yourself that. That's an exercise left to the reader. The second moment of z about its mean is called variance. I like when you have a lecture that starts with something that you haven't seen before and it eventually lands on something that you have seen before. It's got a flavor similar to those stories. And then that little boy grew up to be Albert Einstein. It's one of those situations. So all this craziness that we've been seeing, we're coming back to a word that we hopefully have seen before, which is variance, right? And now here comes another buzzword. We will define the square root of the variance as the, drum roll, standard deviation. Maybe we'll put quotes on that too. And we're going to use the letter sigma for that. And so that is to say that sigma squared is equal to the expected value of z minus mu squared. Oh, you know what? Did I skip something in my last? Oh, I sure did. All right, hang on. I have a mistake in my notes. Let me fix that because I'm trying to like use these again. There we go. You might have caught it, maybe you didn't. This should have a parenthesis and then a power of k. There we go. Apologies. And then, so this would be equal to negative infinity to infinity z minus mu squared p of z dz. That's our standard deviation. So if z is a random variable, then it must be the case that sigma squared is a positive number, which is to say that sigma is a real, because it's not going to be complex or imaginary or anything like that. We should also briefly acknowledge even higher order moments. So one of those is called skewness, is the third moment. Third moment of z about its mean, which deals with asymmetry. So most of us are familiar with a Gaussian or a bell curve. Bell curves do not have asymmetry, but they could. I mean, you could imagine, I should be clear, you could imagine a distribution that does have asymmetry. Gaussians don't have asymmetry. There's another one. The fourth moment is called kurtosis. It's the fourth moment. And it deals with something I'll call peakedness, peakedness, the pointiness of the distribution, essentially. I don't like the way this letter turned out. Let's tidy that up. So the pointiness is the kurtosis. I think the kurtosis sounds like if Dr. Anderson like moonlit as a rock star, he'd be called kurtosis, or maybe a masked wrestler or something like that. I think that's a cool idea. Anyway, not necessarily relevant to this discussion. But we're going to move on and discuss two common distributions, and probably the only two distributions that we're going to use in this course. And those are the uniform distribution and the normal distribution. Those are going to be what we need to know today. So next, we'll consider two common distributions used in navigation. And those are the uniform distribution and the Gaussian distribution, otherwise known as the normal distribution. So we'll start with the uniform distribution. The uniform distribution comes in handy when you have no knowledge between two extremes. So let's draw a picture. And let's say that we've got some value A and we've got some value B, and we know that our random variable is between A and B, but beyond that, we have no idea. So our distribution is going to be a rectangle. And as drawn, the x-axis is the random variable, the y-axis is the probability of that variable occurring. And so if we're going to write this out, this would be a piecewise function, right? P of z is equal to 1 over b minus a in the case where z is between a and b. Oops. All right, tidy that up. Z is between a and b, or it is equal to 0 otherwise. Right. The expected value of z in this case ought to be pretty clear that it's just the average of a and b. A plus b over 2. And sigma squared is equal to b minus a squared over 12. So there's the equation for that. So you've got our mean and our standard deviation of a uniform distribution. And so hopefully that's all pretty straightforward. And that's our entire discussion of the uniform distribution. It's nice to know, but really we're going to be spending most of our time on the Gaussian distribution. And there's a reason why, actually. The Gaussian distribution I should also mention, yes, that Gauss. Remember Gauss's method? Yeah. The Gaussian distribution, also known as the normal distribution, is most commonly used. In navigation. Okay, so this ought to look a little bit familiar. We've got some probability density function. Here comes my best bell curve. Everybody wish me luck. So first, it's going to have some mean. And we're going to start down here. Comes up, peak, down. Good enough. That'll do. All right, I'll take it. And the change in inflection actually happens at the standard deviation point. So I'm going to call this central value mu. I'm going to call this value mu plus sigma, and I'm going to call this value mu minus sigma. That's a minus sign. So we've seen shapes like this before, hopefully, z and p of z. There we go. And so here's the equation. You might have this memorized, you might not. P of z is equal to 1 over the square root of 2 pi sigma squared times the exponential function of negative 1/2, and then in parentheses, z minus mu over sigma squared. There's the Gaussian distribution. Or, because this is a lot, we're going to introduce a shorthand, which looks like this. Z is distributed as the normal distribution with that mu and that sigma squared. So we would actually have numbers there if we knew. So this means is distributed as. And you'll see that actually coming up on, I believe, homework 2 has that is distributed as coming up pretty soon. So you'll notice that there are only 2 parameters in this equation, right? Everything else is fixed. 1/2 is fixed. The value of pi is fixed. We can't play with that. It's parameterized entirely by its mean and its standard deviation, which is to say that if you know two numbers about a particular normal distribution, you know everything about that particular normal distribution. Those are all of its parameters. So we'll note that the Gaussian PDF is described entirely by its mean and standard deviation. That's my shorthand for standard deviation. It's the Microsoft Excel shorthand. So the Gaussian PDF is popular for a few reasons. I feel like I haven't picked on anybody in a while, so I will ask people for their opinions. There's one thing I'm really looking for, but there's a bunch of good reasons why we would want to use the Gaussian PDF. So anybody who's feeling brave and wants to earn some brownie points, go ahead and shout out some reasons why you think the Gaussian PDF is so popular.
I could.
Yeah, what do you got?
Most points are probably centered around the mean, so it's good to use that because with the uniform one, you could pick something at like the very edge of your range and would have the same possibilities being near like whatever the mean is, and that wouldn't really make sense.
Okay, so the way that it's grouped, but I should say this, right? It's not, maybe I should rewind a little bit, make this more clear. We aren't choosing the reality of a random variable. We're choosing how to model a random variable. So we go back to the idea, all models are wrong, but some models are useful, right? So when it comes to your spacecraft state or when it comes to some measurement that you take with a sensor, it really is randomly distributed. There's some randomness going on in there. We don't get to pick that, but we do get to pick how to model it. And navigators seem to have agreed on the Gaussian distribution as being a really cool model. So let me repose the same question, because what you said wasn't wrong. It just wasn't exactly what I was looking for, Merritt. Like, why would we choose to use this as a tool to model things that we don't understand fully? Here, I'll give you a couple freebies here while we're thinking about it. One of them is just that it's easy to define. It's just two parameters. Okay. Another is it has desirable mathematical properties. So for example, if you were to take the Fourier transform of a Gaussian is another Gaussian. That's kind of neat. Another is Gaussian distributions remain linear. I'm sorry. Erase, apologies. Gaussian distributions remain Gaussian under a linear approximation. There we are. My apologies. You can tell my brain's not exactly firing on all cylinders today. But there's one big one, right? I mean, most of us probably learned about Gaussian or normal distributions in high school. Maybe you learned about it in modeling and analysis of uncertainty or MAO, but like they're all over the place. And so like, why are they all over the place? Like, what is it about this function right here? Hang on, this function right there. Why is that all over the place? Why is that so ubiquitous as a tool for modeling things that are uncertain? Any takers? Any thoughts?
Maybe it's because it can give you like a probability for success.
I like that, but there's other tools that we could use. There's other distributions, right? Because you've got the uniform distribution. And I mean, you could imagine any distribution you like, right? The distribution is just the shape of this curve. So what is it about the bell curve shape that has become so ubiquitous? Because I could, just for the sake of the argument, I could say we're going to define the Paul distribution, and it looks like this. There you go. And that's what we're going to use to model this uncertain value. And you might say, no, 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 we're not going to do that. We're going to use a bell curve, right? Because it's more likely that it'll be a bell curve, right? And what I'm saying is like, ooh, nobody asked me why this is so dang popular. Why don't we model things this way? Any takers? I guess this is a weird question because I'm asking you to think about things a little bit differently than you have
I mean,
before.
if you have a good guess, you're going to be centered around that good guess.
Okay, that's pretty
Um,
good. I like that.
some of what Merritt said.
Yeah, it's a good guess as in
What
your
dies off
yeah, it kind of
quickly.
dies off as you move away from some value that it's most likely to be. That's reasonable. I like that. But there is, I mean, here's kind of what I'm looking for. And I guess this is a weird way of asking the question. So, you know, apologies for kind of throwing such a curveball at you, but let's talk about height, how tall people are. If you were to ask a whole bunch of people how tall they are and you line them all up, the probability of somebody being extremely short is low, and the probability of somebody being extremely tall is low, and most people are going to be in the middle. If you were to take test scores and you wanted to model the distribution of test scores, some people are going to do very poorly, some people are going to do really well, most people are going to do about average. If you were to look at, I mean, a lot of things, most things follow this normal distribution. So my reasoning, and I guess this is, apologies for throwing kind of a curveball at you, but the reason I asked such a weird question is like no, it doesn't, basically. Nothing in nature is following this equation, but this equation just so happens to be the best descriptor that we have for things that are randomly distributed. Well, here's the more formal way of writing what I'm trying to say. There's actually a theorem for this, and it's so important I'm going to give a little star here. It's called the central limit theorem. And this dictates that the mean of a sufficiently large number of independent random variables will approach a Gaussian distribution. And so there's a great, well, I'll say one more sentence about this. This is kind of the same idea written another way. In practice, a lot of non-Gaussian error sources contribute to our uncertainty. Therefore, overall error appears Gaussian. So it just turns out that the Gaussian, this, you know, things in nature aren't obeying this equation. They're just doing what they are. But this is the best tool that we've come up with for describing a great number of randomly distributed things, which is very interesting the way it works out that way. There is a great YouTube video that I highly recommend. There's a channel that I highly recommend in general. It's called 3 Blue, 1 Brown. I believe I've already recommended that to y'all, like since we've started in this course. I wanted this one to be brown, but we'll do that. 3 blue, 1 brown. Three Blue, One Brown is a YouTube channel that talks about math, and they have a lot of really cool stuff on there. They have one talking about quaternions. They have one talking about orbit determination, or of a tool that's used for orbit determination. And they have one talking about the central limit theorem and probability distribution functions. And it makes so much more sense the way that Grant, the guy from Three Blue, One Brown, explains things. I like to watch those on my lunch break sometimes. Those are fantastic. So I highly recommend that you check out the Three Blue, One Brown video about the central limit theorem. And I think it will start to make a lot of things click for you that might not have clicked before. But the main point I'm saying here is that basically random variables really be like that sometimes, is my point. So we'll move on to the next thing here. All right. So next idea. This is a good natural pausing point. Actually, are we? Okay, I want to push through one more page of notes and then we'll take a break. I know we're going a little hard today, but after today we'll be back on track with the lecture schedule here. So next idea is called random variables as vectors. Random variables as vectors. So the concepts of mean and variance, by extension standard deviation, can be extended from scalars to vectors. So we'll say let z be some vector z1, z2, zn, and we'll make it a column vector. The mean is mu, with a little vector hat on it now, is the expected value of z, which is written as the integral again, integral again, of the vector z, e of z, dz1, dz2, dzn. Okay, another way of thinking about that is we can say mu is a vector. Essentially, you're going to be taking the mean of each element of the original. So, I mean, this is the fancy math way of saying it, but you could think of it as mu is equal to the expected value of z1, and then the expected value of z2, all the way to the expected value of zn. Still going to be a vector, right? So mu is the mean value of each element in the random vector z. Variance, by contrast, is a bit more complicated. So when you start getting into the idea of a whole vector of random numbers, you can ask a few different things, right? You can consider, so we'll say consider the variance of each vector element. But we can also consider, and this is where it gets different when we get to these higher dimensions, also consider, oh, here comes another buzzword, the covariance between each pair of vector elements. So the variance of Z is a symmetric, positive, semi-definite matrix called the covariance matrix. And that is getting a red underline because of how important it is. If that's the only thing you remember today, it's going to be the covariance matrix, how it's defined and how to compute it, because we're going to be best friends with the covariance matrix for the rest of this course. It's going to be the matrix that tags along with our vector of random variables that tells us, okay, well, you think you know your position, you think you know your velocity, but here's how well you aren't sure. Here's how well you know what you know. Here's how much you're not sure about what you know. So with that kind of mic drop moment, I think that's a good natural pausing point. So we'll break there. It's 5:52 for me, 6:52 for you. Let's come back. So we're going to take a break, 5 minutes. I'll stick around to answer questions, but y'all are dismissed for a bit. Let's come back at it's almost 6:53. So let's say 6:58. And we'll keep moving. All right. Just a quick vibe check before we get started back up. Hope everybody's hanging in there okay. Any burning questions on the stuff we've been talking about so far, or everybody's tracking all right? All right, cool stuff. I think we might have slightly more material than we could finish by 7:30. So I'm going to look for a natural pausing point, and we don't have to finish all my notes today. We can kind of wrap up at the beginning of next time. Y'all were great about staying late last time, and I don't want to make that like anything approaching common. That needs to be a very rare thing that happens. Okie doke. I'm going to start back up again then. So we've just described this covariance matrix. Time to start writing it out. So P is our letter for the covariance matrix, is defined as the expected value of, this is vectors now, Z minus mu transpose. Or you could think of P as containing the expected value of Z minus mu. I guess let's do this way. Apologies. No hats. Nope. I managed that. There we go. Sorry. Z1 minus mu1 squared, and then the expected value of Z1 minus mu1, Z2 minus mu2. You get the idea. Further, this would be the expected value of Z1 minus mu1, Z2 minus mu2 as well. This would be the expected value of Z2 minus mu2 squared. And you get the idea. It's going to be a big old matrix. And we could also call this sigma Z1 squared, sigma Z1 Z2, sigma Z1 Z2, sigma Z2 squared, all the way on down. You get the idea. All right. This is the problem, is like I'm kind of forced to go fast through these sections where I write a lot of equations here. Let me just try to make us a little more space. There we go. So the diagonal terms of the n by n covariance matrix P are called variances, which makes sense, right? So each diagonal term is describing how, essentially, the standard deviation or the variance of the distribution of each term. And then the off diagonal terms, of P are called covariances and are defined as follows. Sigma Zij is equal to rho ij, sigma Zi, sigma Cj, where this term right here, rho Zi Zj, is referred to as the correlation coefficient. Put quotes on there. There we go. That's the correlation coefficient. So I'm going to scroll down a little bit here. And here comes Paul trying to be an artist. Well, wish me luck. So we're going to consider 4 cases. So I've got to do 4 sets of grids here. So we'll consider the case where, and I'll use a different color. Maybe I'll use blue, like blue. Consider the case where if we were to plot, so if this is Zi and this is Zj, and we'll do that for each of these, Zi, Zj, Zi, Zj. So these are both random variables or realizations of a random variable. If Zi and Zj are distributed such that this is essentially a circle, and you can imagine what's really happening is there's points inside the circle, right? If your points form a cloud, you can imagine that this is the case of no correlation. For rho Zi, Zj is equal to 0. No correlation. Where this blue thing here is your data cloud. Data cloud. That's what I'm getting after here. So now, if the distribution of Zi and Zj looked a little bit more like this, we've got elements of the data cloud in here. This would be positive correlation. So if you know that Zi is positive, it gives you the likelihood that Zj is probably also positive. It's positive correlation, or the case where rho Zi, Zj is positive, right? That's the idea. And then you can imagine where we're going with this. We're here. Whole bunch of realizations. This is negative correlation. Or rho Zi, Zj is a negative number. And then you can consider a case where rho Zi and rho Zj, or sorry, where Zi and Zj, there's essentially a line between the two, right? And in this case, we have rho Zi, Zj is equal to 1. And this is what's called perfect correlation, which, as anybody in psychology will tell you, if two variables about personality are perfectly correlated, they're not two different variables about personality. They're the same thing expressed two different ways, right? So the more that we approach perfect correlation, the more we go, wow, these things are so well related that they almost aren't even two different pieces of information. They're actually the same piece of information expressed different ways. Now that's, we're not going to reach that point, but that's kind of what the theoretical limit of this correlation comes down to. So on to the next thing. There we go. Let's consider PDF of a random vector, where, as a reminder, the scalar equation for a Gaussian looks like this. Probability of Z is 1 over square root of 2 pi sigma squared, exponential function of -1/2, and then in parentheses, Z minus mu over sigma, all that squared. All right, that's familiar. We know that already. For a vector, specifically an n/1 vector, the probability of Z, which now has a little vector over bar, is equal to 1 over 2 pi to the power n over 2, the determinant of p to the 1/2 power. Okay, so interesting. So we've replaced sigma squared with the determinant of p. So there's something about the determinant of p that is the vector or the higher dimensional analog for sigma squared, right? Because we're no longer using one number. We're trying to boil down the matrix P into one number to kind of fit the same role here. And then this would be exponential function of -1/2 z minus mu inverse, or sorry, transpose. And now it would be z minus mu transpose z minus mu all over sigma. However, in that case, sigma is a scalar. If we have this as a vector, then we need it to be an inverse, right? Because you can't divide by a matrix, you need to use the matrix inverse. So here we have z minus mu again, and there we are. So this is the same equation, but now kind of scaled up into vector land, or in shorthand, the random vector z is distributed as the normal distribution of mu and p. So you get all the information you need from the mean mu and the covariance matrix p. So the exponent we use the letter phi. So phi of z is equal to z minus mu transpose p inverse z minus mu. So just that from before is called, as a name, the negative log likelihood function. Negative log likelihood function. And the square root of phi of z, in case you care, is called, also has a name, the Mahalanobis distance. Mahalanobis distance, which is the distance from a realization of the random vector z to its mean value mu, weighted by inverse covariance. So you might read the word Mahalanobis distance if you're going out and reading some papers about probability density functions or random vectors. So now you know what that buzzword means. Okay, moving on. For a given distribution, there are a family of values of z that occur with the same likelihood. These values form a surface in n-dimensional space. All right, this is going to sound pretty wacky, but bear with me here. We're actually describing something that you already understand pretty well. Let me just tidy up my all real numbers symbol here, right? N, that's all real numbers to the value power n, so that's n-dimensional space. Since P is symmetric, positive, semi-definite, this surface is an ellipse in 2D, an ellipsoid in 3D, or a higher dimensional ellipse. Essentially, it is an ellipse. All right. Thus, okay, again, this is going to sound pretty weird and mathy, that we're going to draw a picture and it's going to make tons of sense. So just keep bearing with me here. Thus, ellipsoidal surfaces of constant probability are described by all values of z that satisfy z minus mu transpose p inverse z minus mu is equal to k squared. So this resulting shape is what's called the K sigma error ellipsoid. Again, sounding pretty weird. Ellipsoids got some weird functions here. We're going to draw a picture and it's going to make a bunch of sense. And then I think, okay, yep, this picture, and then we've got one more concept and then we're done for the day. All right, the K sigma error ellipsoid. So let's get an example going here. Example, a one-dimensional, a two-dimensional, and a three-dimensional Gaussian distribution. All right. So again, wish me luck. I'm going to draw some pictures here. All right. So we'll consider the one-dimensional case where we're plotting z against p of z, and we get a shape that looks like this. Maybe in this case, I'm going to use black. It's going to make sense why in a second here. So we've got a peak value, it starts to taper off. Pretend I drew this symmetrically, right? We're gonna chalk any asymmetry up to problems with me. And let's say that this is 1 sigma here, and then I'll use maybe green for 2 sigma, and then I'll use red for 3 sigma. Okay, and go back to the middle. So the middle value, I don't want to do this. I'm going to just do this for now. See, I have the logic of just doing Control Z. Y'all don't, so I'm trying to be like aware of that. So this middle value is mu. You can just kind of find some room for that on your page. And then this blue region, you could think of this as the 1 sigma region, right? It's the region where if you're in that region, you're within 1 standard deviation of the mean. Then if you come out here, this is a 2 sigma region. You might be familiar that 1 sigma is, I believe, is it 63% of the distribution is within 1 sigma, and then it's like 95%, and then finally it's 99 and even higher percent when you get out to 3 sigma. This is 3 sigma. Okay, so that's one-dimensional. Hopefully that makes sense. So now, if I plot, this is going to be 2-dimensional. If I plot z1 on the x-axis, z2 on the y-axis, and pz is coming out of the screen or out of the page, just imagine that it's a 3-dimensional plot now, then these lines of constant probability become ellipses of constant probability. So let's say that you've got some 1 sigma ellipsoid, which looks like this. And then we've got a 2 sigma ellipse, which looks like this. And then we've got a 3 sigma ellipse. Yes. Nope. Okay. Tried my best. Oh no. I like that one. Put it back. Oh wow, it's gone, isn't it? Okay, there we go. I recovered it. All right. This is computer assisted drawing because I need all the help I can get. All right, there we go. Nice, we did it. Very sigma. There we go. And you can imagine in this case that the very center of this distribution is the vector. Oh, hang on. Is the vector mu. Okay. And now we can also scale this up to 3 dimensions. So in this case, let's say that we've got Z1 on this axis, Z2 on this axis, Z3 on this axis. It's getting trickier and trickier to describe what's actually going on here because now they're going to be shells of constant probability. It's not going to be blobs of constant probability. It's actually going to be like a 3-dimensional. So I'm going to try to draw this as sort of like a football type shape here. So imagine that you've got some shape that's actually got depth and roundness to it, right? And that's going to be our 1 sigma. And then if we go out to green, going to be a larger shell surrounding this. Where, there we go, look a little bit like that. And this will be 2 sigma. And then finally, we get an even larger shell. Wow, I can do better than that. All right, let me try that again. For whatever reason, it's the red one that always seems to get me here. Good enough. You've got this even larger red shell, which is your 3 sigma ellipsoid. And it's not exactly obvious in the way I've drawn it, but it's meant to be an ellipsoid. It's a triaxial ellipsoid. And then the point in the very center is, again, the vector mu. Okay, so I'm going to scroll down a tiny bit. As drawn, first of all, I'll make a note. As drawn, all distributions are 0 mean. If the mean is at the origin, it's a 0 mean distribution, right? So for a 1D Gaussian, contours of constant probability are points on the z-axis. Right. For a 2D Gaussian, contours of constant probability are ellipses. And I like to refer to this as a dartboard. Obviously, well, not always, but if you throw a dart at a dartboard, you're typically aiming for the bullseye, not if you're like playing the game darts and you're shooting for an actual number, but just let's pretend, right? You're trying to demonstrate that you have good aim. You're aiming for the bullseye. So the mean, if you were to lob 100 darts at the dartboard, the mean would be the bullseye, because on average, that's where you're hitting. But the covariance or the standard deviation has more to do with the region of the wall that you're hitting. Ideally, it would all be on the dartboard. If it's me, I need to go buy some spackle to fill in some holes. So I have run into that problem before. And then in 3D, contours of constant probability are ellipsoids or shells. And I think of this as like Russian nesting dolls, Matryoshka dolls. That's how I think about it, at least. So you could think inside of the 3 sigma ellipsoid is a smaller 2 sigma ellipsoid. Inside of the 2 sigma ellipsoid is a smaller 1 sigma ellipsoid. So when you're computing something like, say, the position of a spacecraft, we think we know the position of the spacecraft, that's mu, but we are reasonably certain that it's inside the 1 sigma ellipsoid. We are quite certain that it's inside the 2 sigma ellipsoid, and we're much, much more certain that it's inside the 3 sigma ellipsoid. So there are requirements, and you'll see, you know, if you get into guidance, navigation, and control, requirements documents that say you shall know the position of your spacecraft. 3 sigma is less than some value. So you're not only do you think you know it, but your uncertainty has to be beneath some value, that sort of thing. In the case of 2D, there's a group that is in the same branch that I work with that computes the mean and the standard deviation, or the covariance, of the region where we think the Orion vehicle is most likely to splash down when it comes back from space. And so there's a mean, like we think it's going to land here right next to the aircraft carrier, but it could be anywhere within the 1 sigma, the 2 sigma, the 3 sigma ellipse. And so that gives us information about where to put boats and where to put rescue personnel, stuff like that. Because they're computing a quote unquote footprint, or a region of the surface of the water where we think the vehicle is going to come down, the team has called itself the Sasquatch team, because they're always computing a footprint. I think that's funny. But it's the same idea, right? It's the distribution in 2 dimensions or in 3 dimensions of the uncertainty of something. And that's not quite as far as I would like to have made it today, but hey, that's life. I think that's a good natural stopping point. Next time, we're going to talk about eigendecomposition, and then we're going to get into the next topic, which is mathematical techniques in estimation theory that we can use to estimate values, things like least squares and maximum likelihood estimation. You might have heard of those before. Anyway, I'm going to stop the recording, and y'all are dismissed, but if you want to stick around and ask any questions, I'll be here for a little bit.